All right. So, pretty pictures indeed. I am Jasper Bekkers. I founded Traverse Research in 2019. We're located in the Netherlands, in Breda. And we do research on sort of graphics workloads and graphics hardware and all that kind of stuff. So we try to, develop forward-looking workloads, benchmarks, and do a bunch of things. We have big ties with some universities. We're into sharing, collaborating, and doing research like this. And the kind of work that we do is split up into sort of three pillars. So there's a GPU benchmarking pillar, meaning we work with hardware vendors to prove out sort of their ray tracing implementations or see that like new upcoming features, maybe work graphs are fast enough or to their liking on their specific implementation, and that includes sort of pre-silicon and post-silicon benchmarking and workload generation. Then there's graphics research. So there's a bunch of research that we do also in the machine learning space where we try to integrate ML into a game frame, which we don't see a lot of people focus on. And then there's like bespoke development that we do together with hardware partners or other partners. Anyone who would take a picture? You heard the click. So most of the presentation will be about the new benchmark suite that we have up and coming. Darius will take over at some point and talk a little bit about some of the more technical details. But Tom was talking a lot about evolving Vulkan and evolving and things growing. We have a benchmark suite that's called Evolve, so thanks for the plug, Tom, even if it was not intentional. The benchmark suite focuses a lot on ray tracing, path tracing. It's implemented in Vulkan, DirectX, and Metal. And it has all of our effects implemented both as ray query and ray pipeline. So that has proven to be useful for some vendors already. The work that we're doing, for a large part, sits on top of a sort of common engine that we developed at Traverse that will be open sourcing. I'll talk about that later. One of the things that's sort of different about Evolve is that we score, let's go here. Because I kind of talked over this and then didn't skip to the slide. So we have a path tracing hybrid render, runs on mobile platforms, also runs on desktop. Obviously, we tweak the content for each to make it look good enough to our standards. The screenshot is really dark on the projector, but trust me, it looks good. It's a vegetation-based demo because obviously we all know the pain of ray tracing vegetation with alpha-tested foliage. And then we try to score the run in various ways. So score based on acceleration structure build times, score on ray tracing times, rasterization times, compute. We have an energy score even on Android on devices that support it, which is 1. But at least we can do it. And we score driver overhead because we noticed that some vendors spend a lot of time in various driver calls. For example, build acceleration structure driver calls that we also want to sort of inform consumers about. We focused on like really delivering stats for nerds. So like at the end of the benchmark run, you get to submit your scores and you get to compare them against all the other ones on the various different categories. So there's not one single score at the end, which should help with your like internal KPIs or external KPIs and ways of communicating around hardware performance with potential customers. And we'll have like an online leaderboard, of course, because that's what every benchmark does. Here you see sort of a breakdown of one of the categories of the scoring. So this is a breakdown, I think, of the sort of high-level ray tracing score, and we'll run through various effects. It has Restore DI in there. That doesn't actually take 27 microseconds. It's disabled in the scene, so that's why it shows up like this. But it gives a bit of an overview, and I think this is the old categorization because it says compute score and it has culling in there. But this should give you a bit of an overview. And this is where I hand it off to Darius to talk a little bit about sort of implementation details of the framework, the benchmark suite, and how we use Vulkan, because I think that's also pretty interesting for folks here.
Yep. Hi everyone, I'm Darius. I'm a rendering engineer at Traverse Research, and I'm just going to go over like some of the core features of the Evolve benchmark. So obviously we have a path tracer, which is primarily focused on a wavefront path tracing style. But we also support a recursive pipeline tracer. And besides the path tracer, we have a hybrid renderer, which is like ray trace global illumination, ray trace reflections, ray trace soft shadows, as well as some custom material models. Sadly, I'm not going to talk a lot about the GI stuff, but I'm going to talk more about the engine usage from a user standpoint and how that ties up with Vulkan as well. So. Yeah, as I mentioned, the path tracer is a wavefront style. It supports both pipeline tracing individually and inline traces. Again, pipeline, recursive path tracer, and also doing some radiance caching along the way, because why not? We're doing real time. So we have actually several radiance caches working. So one is the clip map radiance cache, a hash grid-based radiance cache, and also a neural radiance cache, and that's all running for the path tracer and for the hybrid renderer. So the hybrid renderer, it's featuring, well, basically we restir everything because it works really great. For GI, for reflections, we also ray trace the refractions and ray trace the soft shadows, and we fitted a conductor material for the metallic BRDF. So, let's cropped a little bit. So for engine development, this is actually how we set up just a basic compute pass. On the top, we have like a YAML definition where we just declare like the source location of the shader and the entry point. It's pretty straightforward. And then on the CPU side, we utilize a random graph for everything. So the user doesn't have to worry about any explicit syncing, no barriers, no resource lifetime tracking, because that's all kind of stuff like if you do it once correctly, you don't have to do it ever again. And we don't want to bother users with the kind of management. So we pass in the resources, and these are matched one-to-one against the shader counterpart, which I'll go on to later. So before going into the shader side, we do everything bindless. And this was kind of an interesting journey for Vulkan specifically, because we don't have resource descriptor heap quite yet. So we have our own abstraction for that. And this is kind of the foundation of that. And for resource, for descriptor indexing, we don't want to use all the 32 bits to just index an array that's maybe 10,000, maybe 100,000 resources if you're pushing it. So we're using different bits to indicate what kind of a resource it is, what kind of a version it has. So a version is essentially meaning what is the lifetime, and if the resource is actually read-only or not. And that is a foundation for also validating this usage. So behold the beautiful templating magic of abstracting it for bindless. So in order to make this work for DirectX 12, Vulkan, and Metal, etc., we need to abstract how we actually access the resources without exposing it to the user. So we made some explicit resource types that we just, yeah, I can imagine, abstract everything that the HLCL spec has for resource access. So that was quite a bit of typing. But we use an emulated resource descriptor heap for Vulkan. And that basically comes down to this. We use register overlapping, which I didn't fit into this slide, but we use a little trick where we just template each type to give it like an explicit access type, and then we add operator overloading to a structure. And it's not really needed to go this far to get it working, but it was nice to make it sort of array indexing uniform between Vulkan and DirectX 12. And that ends up with a very simple shader where we have a structure of our bindings, our resources. We can add in constants as well. You can mix and match and do whatever you want with it. So yeah, you can just, for demonstration, it's just very simple. We just store a 1 into a texture, and we access that from bindings itself. So there's no user-defined bindings, no register definitions, and nothing. But then again, this is prone to error because the user can just put in whatever you want, right? And then maybe pretend that there's another buffer at the end here. But luckily, we have some validation for that. Again, going back to the resource handle, we don't use the full 32 bits as an array index. We use it for the tag and the version, and if it's writable or not. So at runtime, we can just, at a very, very low cost, actually validate all of the usage. So if there's a mismatch in like the size of the bindings, if there's a mismatch in ordering, it instantly gets caught by the validation system, which validates it on the GPU. If a invalid user is detected, it writes a simple small packet back to the CPU. And that actually caught almost all of our access bugs, or crashes, and etc. And with that, I will give it back to Jasper.
Thanks. So once we release Evolve later this year, we will start a big push to also open source the Breda framework. It's a big Rust code base that allows you to sort of build cross-platform applications. Is actually easy to develop on Android with this, which is kind of nice, and that's messed up. Well, here are some of the features. It has a very strong focus on ray tracing, simply because we had a strong focus on ray tracing, and it has a very strong focus on sort of high-performance graphics and high-end graphics. But small set of features. These are some of the bigger features. So things that will not appear in the benchmark suite just yet due to lack of time, but will end up either in a later iteration or in a open source release, are, for example, volumetric rendering. So we support parsing and loading and rendering VDB files, for which we had to implement some stuff. There's a machine learning framework in there that runs inference and training, and you can run it on the shader cores. It specializes in the tiny networks, so no big sort of llama-style networks, but networks that like would be suitable for a game, so tiny MLPs and that kind of stuff. Denoisers could work and have worked actually. It is fully in software at this point. We're working with vendors to make it hardware accelerated. It supports a subset of ONNX to load in and then run on your GPU. And it's at this point, I think it's still FP16 only. Maybe FP16 and FP32, but depending on how the hardware acceleration goes together with partners, we will add FP8 or smaller. There's a small nerf example in there that's pretty fun to look at, but we've all seen the nerf demos. They don't typically look very good, at least the initial basic instant NGP style networks. We have a neural material implementation in there, which is it's research we published on SIGGRAPH Asia 2022. And in this scene, the full scene is path traced, and then it's integrated with the neural materials. So the leather on the chair is a neural material, and we've shown like some cases where it looks really good, and some cases where it just looks okay. We have some research into path space denoising, probably will also be in there. And some texture compression that is very similar to what Kartik had published about earlier. There's some other things in there as well that maybe some people have seen these slides, some people haven't, but the picture for the water simulation doesn't really do it justice. We actually have a sort of full fluid sim, I think it's 2D and 3D. And then the ML part of the fluid sim is, I think, also only in 2D. But I wasn't quite sure. So we were trying to do like ML for fluids. Here we have some other screenshots, still quite dark. If you want, come take a look on my laptop later. It looks a bit better. And there's some other screenshots. So these would be part of the sort of fly-through that the benchmark runs through. And that's all for us. So feel free to take a picture, scan the QR code. It points you to our website. It doesn't point you anywhere strange. And that's it. On to the next.